Hi and welcome everyone. In this video, I want to talk about differentiability. Basically, we're going to examine when a function is differentiable. Differentiable, that means the derivative exists at a point. Before starting differentiability, have a recall here. We talked about continuity. Continuity, we said f of x is continuous at x equals to a if the limit as x approaches to f of x equals to f of a. So we went over this. Now we're going to talk about differentiability. F of x is differentiable at x equals to a if f prime of a exists. Or in my last video, I talked about those two limits. You find f prime of a by doing the limit of f of a plus h minus f of a over h. That's going to give you f prime of a, or you can use this one, whichever one works better for you. Limit as x approaches to a of f of x minus f of a over x minus a. So if these two limits or either one of them exist, then you can say that f of x is differentiable at that point, or you can find the derivative. And also remember, f prime of a is the slope of the tangent line at x equals to a. Now, these are examples. I put some examples for you where f of x is not differentiable. What happens to the graph? So the first one case you can have, this is our graph. Here we have a corner. But in reality, what happens, the slope of the tangent line from the left side, this is the line. And from the right side, this is the line. The slope of these two lines are not equal. Or if you write that, you can say limit as x approaches to a from the left side of f prime of x is not the same as limit as x approaches to a from the right side of f prime of x. Next one, it's pretty obvious. If a function is not continuous at a point, then automatically it's not differentiable. So this function is not continuous. So if you find the slope of the tangent line here from the left side, you're going to get, this is the tangent line, and here this is the tangent line. They're not going to be the same, so therefore it's not going to be differentiable. And finally, the third case happens when you have a vertical tangent line. So here the tangent of a vertical line is undefined. So here I put for your vertical tangent line, or you can check that limit as x approaches to a of f prime of x, or absolute value is going to give you infinity. And again, this point is a also. Now let's go over some examples. So let's say we have this function f of x equals to cube root of x, and we know that cube root of x is the same thing as x to the power of 1/3. And we want to find f prime of x. Now I did this two ways. One, that's easier to use this limit as x approaches to a of f of x minus a over x minus a. And if you substitute, again, if you try to find the limit, the top is going to be 0 and the bottom is going to be 0. So it's indeterminate form. Now, what we can do here to find the limit, we know that x minus a can be written as x to the power of 1/3 cubed minus a to the power of 1/3 cubed. And this is the difference of two cubes. And we can factor that by writing x to the power of 1/3 minus a to the power of 1/3 times x to the power of 2/3 plus x to the power of 1/3 times a to the power of 1/3 plus a to the power of 2/3. This is from algebra. That's how you factor the difference of two cubes. So remember, from algebra, the difference of two cubes can be written as a cubed minus b cubed is a minus b times a squared plus ab plus b squared. So now why did we do this? If I take that, and I can write that as x to the power of 1/3 minus a to the power of 1/3, and instead of x minus a, we can write this as x to the power of 1/3 cubed minus a to the power of 1/3 cubed. Now we can factor this by using again the difference of two cubes, or that formula. So that can be written as x to the 1/3 minus a to the 1/3 times x to the 2/3 plus x to the 1/3 times a to the 1/3 plus a to the 1/3. And these two are going to cancel. So what's left is 1 over that expression. And if we substitute all the x's by a, and we simplify them, so the bottom, just notice that a to the power of 1/3 times a to the power of 1/3 is a to the power of 2/3. So these are all the same. If we add them, we get 1 over 3 a to the power of 2/3. If I want to write the general formula for the derivative, I can say f prime of x equals to 1 over x to the power of 2/3. Now this is a good formula to use, and that's what I use to find the limit. But if you want to use the other one, so if you want to find the limit by doing limit as h approaches to 0, f of x plus h minus f of x over h. So same thing, if you substitute x by x plus h, then you get x plus h to the power of 1/3 minus x to the power of 1/3 over h, and you do get 0 over 0, which is indeterminate form. Now this is a little bit tricky if you want to find the limit this way, but let me go ahead and explain. What you can do, you can multiply top and bottom by x plus h to the power of 2/3 plus x plus h to the power of 1/3 times x to the power of 1/3 plus x to the power of 2/3. So same thing to the denominator. But that expression, again, this is the factor of the difference of two cubes, and this is x plus h minus x. So this is our a, and that's our b. So actually this is our a, and this is our b. So if you multiply, distribute all that, you are going to get x plus h minus x. And x's cancel, and you can cancel here the h's, so you're left with that. And if you substitute h by 0, you do get 1 over 3 times x to the power of 2/3, which is the derivative. Now for the same problem, if I want to find f prime of 0, f prime of 0, I have f prime of x. If I put 0, I get 1 over 0, which is undefined. If it's undefined, then just go ahead right away, try to find this limit. Limit as x approaches to 0 of f prime of x, or absolute value of f prime of x. And if we do that, we're going to get positive infinity. If you get positive infinity, that means we have a vertical tangent line at that point. The graph of f of x equals to cube root of x is that. And we notice that at 0, we do have at this point the vertical tangent line because the derivative is undefined. Now I have a second example for you here. Absolute value of x minus 6. So it says show that f of x is not differentiable at x equals to 6. Use the definition of absolute value. Absolute value of x minus 6 can be written as minus x minus 6 if x is less than 6, and x minus 6 if x is greater than or equal to 6. So basically this is 6 minus x, and that stays as x minus 6. So the function can be written as 6 minus x if x is less than 6, and x minus 6 if x is greater than or equal to 6. Now we're gonna use again the limit definition and then just use this one. If I want to find f prime of x first, here we have this is a piecewise function. So first we're going to calculate the limit as x approaches to 6 from the left side. So we do take that top function of f of x minus f of 6 minus x over x minus 6. So it's going to be 6 minus x minus 6 minus 6 over x minus 6. And if you do that, then you get -1. If you do the same thing from the right side, then you use this function. So it's going to be the same thing, f of x minus f of 6 over x minus 6. But here you pick x minus 6 minus 6 minus 6 over x minus 6. And if you do get, you get +1. Basically, the slope of the tangent line from the left side is -1. And from the right side is +1. So we know that this does not exist because the two limits are not the same. And f prime of x is -1 if x is less than 6, and it's 1 if x is greater than or equal to 6. So you say f of x is not differentiable at x equals to 6. If you graph absolute value of x minus 6, this is the graph of absolute value of x minus 6. And you notice that from the left side, we have the slope of that line is -1, and from the right side is +1, and they're not equal. And that's the case where you have a corner. So we did the two cases. The first case, if I go up, so we saw that, which is for absolute value of x minus 6, and then we saw this one for when the function, when we have a vertical tangent line, so that's for cube root of x. Now, I do want to go over this theorem with you. So we know that if f of x is not continuous at x equal to a, then f of x automatically will not be differentiable at x equals to a. However, if f of x is differentiable at x equals to a, then for sure f of x is continuous at x equals to a. So if a function is continuous, is not necessarily differentiable, like this one. This function is continuous at 6, but it's not differentiable because it's a corner. But if a function is differentiable, it's automatically continuous. And let's go over the proof of that. So we know if a function is continuous at x equals to a, we have to have that. So if the function is differentiable, and from that we can show that this is true, then we can say that the function is continuous. Now we know if a function is differentiable at x equals to a, we have that limit exists, and f prime of a can be written as limit as x approaches to a of f of x minus f of a over x minus a. Now let's do some manipulation here. Just write f of x minus f of a. And you can say f of x minus f of a is the same thing as if you multiply top and bottom by x minus a. So you just bring x minus a. So they cancel and you're going to get the same thing. But let's add this to multiply the numerator by x minus a and the denominator by x minus a. Now, if you want to find the limit of that as x approaches to a, we can write it limit as x approaches to a of f of x minus f of a. Then we can use that. So that's the same thing as saying limit as x approaches to a of f of x minus f of a over x minus a times x minus a. But we all know that is just the derivative of the function at x equals to a, or it's f prime of a. And that's times x minus a. And if you put a here, you get the answer is 0. Now, why did we do that? Now we can write limit as x approaches to a of f of x. We can write that as limit as x approaches to a of f of x minus f of a plus f of a. We can just subtract and add. These are, f of a is a constant. So that expression can be written as limit as x approaches to a of f of x minus f of a plus limit as x approaches to a of f of a. But we found that that limit was 0 from here. So it's going to be 0 plus, and the limit as x approaches to a of f of a, that's a constant. So that's just f of a. So it's going to be f of a. And guess what? Limit as x approaches to a of f of x equals to f of a. So therefore, f of x is continuous at x equals to a. So that shows if a function is differentiable, we started from this limit. And we showed that from here, by doing all these manipulations, we can get limit as x approaches to a of f of x equals to f of a. Therefore, f of x is continuous at x equals to a. So remember, at a point, if a function is continuous, it's not necessarily differentiable. But at a point, if the function is differentiable, then it's for sure continuous. So please do more examples on this and watch this video 2-3 times. And in the next video, I'll talk about the differentiation rules, the power rule, the product and the quotient rule, and do some examples for you. Thank you for watching, and I'll see you in my next video soon. Have a great one, everyone.